Hello, class. This is Mr. Hart. And in this podcast, we want to continue our unit on energy and think more about energy transfer and how energy moves between different forms. Specifically, we're going to focus a lot on the conceptual side. We're not going to do any calculations today, but we're going to figure out ways to accurately describe how energy is moving between places. Okay. Now, one of the ways we can do this is with what is known as a energy bar graph. Okay, so let me kind of give you an example of what this looks like. So let's say we know that in our system we have a certain amount of potential energy to start. Okay, like the book falling off the shelf example we've done many, many times. Okay, I could represent that with a bar that shows how much amount of energy is stored in potential. And let's say we don't have any kinetic energy to start. Okay, the book is sitting on the shelf. Then as it falls, okay, we know at the end it has all kinetic energy and no potential. But what does it look like in the middle? Well, if this is our starting setup right here, okay, our initial state, then maybe halfway through, we can call that our final state, even though it's not the final setup. But halfway through the middle, what does that look like? Well, without doing any calculations, it's halfway in height, so it should have about half the potential energy as it did before, right? Well, where did that energy go? Well, it's not potential energy anymore, so it must have gone to kinetic energy. Okay, so this is a very simple example, but we're going to look at how we can show with these bar graphs where the energy is going. Is it going from kinetic to potential, or potential to kinetic? What forms of potential is it going to? And so forth. Okay. So these are the types of problems you'll see. Okay. And you'll see these on your homework. So we have these plots over here, and then we have some scenario. Okay, so here's our example problem. A car, having just run out of gas, coasts uphill to a stop. Okay. So to start with, what type of energy does this system have? Well, if we're going to fill it out, let's say that it starts with all kinetic. Okay, they do E sub k, meaning kinetic energy. Okay, we don't have any gravitational or potential energy. We don't have any spring or elastic energy, and we haven't lost any energy to friction. Okay, now assuming this is completely frictionless, okay, that car will coast uphill and go 10 feet in height, right? Now, we know it comes to a stop, so there's no more kinetic energy. That has gone to zero. And we didn't lose any energy to heat, so we'll assume that the rest of this energy went to gravity. Okay? So it runs out of gas. All that energy is now stored in potential energy as it's up on the hill. Okay? What if we did say there was friction? What if we could lose some energy to dissipated? Well, all that means is some of this energy would get chopped off, some of it would go to gravitational, and the rest of it would go to dissipated. Okay? Now the key here is as long as the same number of bars is filled up here and down here, initial and final, then energy was conserved properly. I had 4 bars of energy here. I have 3 plus 1 bar of energy here. Energy is shown to be conserved. Okay? So that's the idea of these energy bar graphs. Okay? Keeping the system consistent, showing that the energy is just flowing between different forms. So let's go ahead and have you try and do a problem on your own. Okay? Here's the graphic for it. I'm going to change it a little bit so it's a little bit different. Let's say there's a spring that the car is launching from. Okay, so it starts with 0 velocity, okay, and it goes some height and is moving some distance, okay. So sorry, I changed this one a lot in class, okay. So the car is at 0 velocity, 0 height, you put it on this spring and you launch it, okay. It moves a certain height, it moves a certain velocity, and there's some friction. What would this look like, okay? Well, to start with, all of our energy is stored in elastic energy, in spring energy. So our initial graph, okay, will just be all elastic. elastic energy. Okay, that's the only energy we're looking at. Then it goes uphill. Okay, it's moving a certain velocity. It lost some energy to friction. There's a couple ways we could show this because there's not any details, but here's the key. We gotta have 4 bars, right, to end with. So let's give 1 bar to kinetic energy because we know it's going to be moving. We'll give 2 bars to gravitational energy because it looks like it's gone a pretty high height. Okay, and some of that will be lost to dissipated energy. Okay, so there's many answers that would be correct for this type of problem given the details, right? But the key is we started with elastic energy loaded on the spring. It gets launched, it gets some kinetic energy, it gets some gravitational energy, and it loses some energy to heat. Okay, but again, energy is conserved because we got 4 bars to start and we got 4 bars to end. Okay, and that's it. So that's one way we can represent conservation of energy is through these bar graphs showing where the energy flows. Okay, another way we could do this is through what I call energy transfer graphs, okay, or energy transfer flows. There's not really a good word for it, but just basically writing out where the energy goes in each setup. Okay, so let's consider a car engine, for example. Okay, you start the car with some electric igniter. The igniter goes to the gasoline and ignites the gasoline, and that moves the car. So you could describe that energy flow as having some type of electric energy. Okay, you start the electric igniter with your key. That moves and then ignites the chemical energy that's stored in the gasoline. And that gasoline then explodes, right? Causes thermal energy. It has that heat energy that comes from the explosion of the gasoline. And that in turn moves the piston, right? Which then moves the car. So obviously this is not 100% transfer, but you can think of it as electric energy moves to chemical energy, which moves to thermal energy, which moves to kinetic energy. Okay? And again, this is one of those things where you could have many different answers and you could have different perspectives on how you describe it. But the key here is just writing out different types of energy you have and how they're flowing to it. Okay. Another example you can think of is, let's say you are turning on a stove, okay, and boiling water. Okay. Now, depending on what type of stove you have, it could be electric or gas. Let's say it's electric, so you turn a knob, right? So again, starts with electric energy. That electric energy, goes through the coils and starts to heat them up, which turns it into thermal. Okay. That thermal energy then heats up the water, which then turns to kinetic energy. Okay. So again, kind of a similar flow, electric to thermal to kinetic. Okay. And so that's all we're doing is just describing what types of energies are present as a event is happening or occurring. Okay, so that's another way we can describe energy transfer flows. Okay, the last kind of energy graph you'll see is what we call a energy time graph. Okay, which is kind of your standard plotting graph from math, where you plot the energy in joules compared to the time in seconds. Okay? And so let's say this is your potential energy in white right here. So this could be like an object falling off a cliff. Okay? It wouldn't fall straight down like that, but you have some potential energy that you are losing over time. Well, if energy is conserved, then that means that something else must be gaining that lost energy. Okay? For simplicity's sake, let's just say it's kinetic energy. Okay? So if the potential energy graph looks like this, the kinetic energy graph must be able to match it. Okay? It's going to go in the opposite direction, okay, to match the graph. Okay? So as potential energy goes down, kinetic energy is going to go up. And the cool thing is that the potential energy and the kinetic energy will always add to the same amount each time. Okay, you can see that with this graph right here. Okay. As potential energy goes down, kinetic energy goes up. But if you add the two at any point along this graph, the total energy stays the same. They'll always add to a single value because energy is conserved. You're not going to gain or lose anything as it's going through this process. Okay? So, let's look at this scenario. Graph the kinetic energy for this potential energy graph. So while we're doing this, we got to keep in mind that the total energy must add to a fixed amount. So if that's the case, at the very beginning, it's going to be really low. At the very end, it's going to be really high. And in the middle, it's going to kind of intersect and match the shape of that graph. Okay. Now that's not the best drawing in the world, but you can imagine it's kind of mirrored, okay, the mirror image of the potential energy graph, okay, but going the opposite direction. Okay, that's the kinetic energy. Okay, let's do this one. Okay, what's the kinetic energy graph in this scenario? Well, same thing. It'll start out low. It will go high. It'll come back down when the other one goes up. It'll go up when the other one goes down, and mirror it like that. Okay, so that's all you gotta do is keep the energy addition the same. Okay, so it'll look something like this. It doesn't have to be perfect. But just, again, the concept of showing that the energy is conserved in the system. Okay? Awesome. So that's all we're going to do for this lesson. So we looked at the 3 different ways we can represent energy. We can do energy bar graphs, energy flow, and energy time graphs. Okay? So that's what you're going to be practicing on your homework. Hopefully that all made sense. Let me know if you have any questions, and thank you for watching.